Good evening, everyone. I'm going to share on carbonyl compounds. It's not a very long presentation, so please bear with me. Here are the learning outcomes for this chapter. Now, these are examples of carbonyl compounds found naturally. Okay, and for carbonyl compounds, we look at two types: aldehyde and ketone. Aldehyde are compounds with the general formula RCHO, where the CHO is termed the aldehyde group. So this R here could be either H, alkyne, or arrow group. Aliphatic aldehyde means that R is an alkyne group, and sometimes we could have aromatic aldehyde where R is a arrow group. There must be at least one H atoms attached to the carbonyl carbon atom. Okay, so if you have at least one H bonded to this C, that's also bonded to O, this is an aldehyde. But if you have this, the two substituent bonded to C is both alkyne or arrow groups with no hydrogen, then this is ketone. For aliphatic aldehyde, the longest chain carrying the CHO group is the parent structure and is named by replacing the E with the corresponding alkane by Al. The position of the substituent is indicated by a number. The carbonyl carbon is considered carbon-1. For example, we have methanol, which is also known as formaldehyde, ethanol, X-taldehyde, hexaldehyde, propanol, butanol. And we have this as the aromatic aldehydes, 3-phenylpropanol. Okay. So for aromatic aldehyde, the CHO is bonded directly to the benzene ring. The parent structure is named as a benzaldehyde. The carbon on the benzene ring bearing the carbonyl functional group is considered carbon-1. And the position of the substituent on the benzene ring take reference from this. So if this is 1, this is 2, 3, 4, this will be 4. Okay, we call this 4-bromo-benzaldehyde. Ketone, the name is obtained by replacing the final E of the name of the corresponding alkane with ONE. The chain is numbered such that carbonyl carbon atom has the lowest possible number, and this number is used to indicate its position. For example, propanone, butanone, pentatone, pentatrinone. Propanone has another common name called acetone. And we also have this compound called cyclohexanone. So to name the compound, for example, we have identified this longest continuous carbon chain to be 4. So it's butanol because you have the C bonded to H here. So it's an aldehyde. You have a substituent here. So this is the first carbon, second, third. This is methyl. So it's 3-methyl-butanol. As for here, you have 1, 2, 3, 4. You have 4 carbon in the longest continuous carbon chain. We call it butanone, is an ketone. So this benzene ring is attached to the third carbon. We call it phenol, 3-phenylbutanone. So these are the ways we name a ketone and aldehyde. So the benzene ring is a substituent in that case. But it really depends. If the CHO is directly bonded to the benzene, then the whole thing is benzaldehyde. Okay? Now, as polar molecules, aldehyde and ketone have higher boiling point than alkanes of similar cloud size. So similar electron cloud size means similar number of electrons, which means similar value of MR, relative molecular mass. So we will compare between these three and observe that butane 1-nol, the alcohol, has the highest boiling point because there is hydrogen bonds between the molecules, stronger and require more energy to break, compared to PD-PD between butanol molecules and ID-ID forces between pentane molecules. Okay. As for solubility, the lone pair of electrons on the carbonyl oxygen atom, if you observe in this structural formula, it allows the carbonyl compound to form hydrogen bond with the H atom of the water molecule. But it cannot form intermolecular hydrogen bond within itself or intramolecular. So it can form hydrogen bond with water, but by itself cannot. Okay, so this ability to form hydrogen bond accounts for the solubility of short chain carbonyl. I need to emphasize short chain. Okay, this is because when the length of the carbon chain increases, the solubility in water decreases due to increasing size of the hydrophobic alkyne group. Okay, emphasize on this. So if your carbon chain length becomes longer and longer, the molecules become more non-polar. Okay, the ID-ID interaction become the predominant intermolecular forces. Okay, so that will decrease the solubility of the longer chain carbonyl compounds. So carbonyl compounds in general have good solubility with a shorter chain, but as the chain gets longer, the solubility decreases. However, they do form good interactions with non-polar solvents. For example, acetone is used as an organic solvent to clean apparatus in laboratories and is used in nail polish removal. Now, let's look at how carbonyl compounds are prepared before we look at the reactions later. So the type of oxidation products obtained depend on the type of alcohol and the strength of the oxidizing agent. We did cover parts of it under the topic of alcohol. So in the topic of alcohol, we talk about primary alcohol is oxidized to aldehyde. Okay, if we want to prevent further oxidation of aldehyde to carboxylic acid, okay, we need to do immediate distillation. Okay. As for secondary alcohol, it will be oxidized to ketone and will not be oxidized further. So that's what we have covered earlier. We try not to use KMnO4 in the oxidation of the primary alcohol if we want to form aldehyde, unless we want to form carboxylic acid. If not, then we cannot use KMnO4. It will cause the reaction to proceed all the way to formation of the carboxylic acid. So this reaction mixture will be kept at a temperature below the boiling point of alcohol and above aldehyde, so that the aldehyde is distilled off when it was formed. So when the boiling point of when the temperature is kept above the boiling point of aldehyde, the aldehyde will be able to separate out from the alcohol. So let's say you have boiling point of alcohol. Then you have boiling point of aldehyde. Okay, so if your temperature is set in between, okay, so my apology, this should be alcohol and that should be aldehyde. So if below the boiling point of alcohol and above the boiling point of aldehyde, because alcohol have a higher boiling point due to the stronger hydrogen bond. So if that happens, then alcohol will be, because the temperature is still below the boiling point, so it is, this one remain as a liquid, this one remain as a gas. So the gaseous aldehyde can be distilled off away from the liquid alcohol. All right. So this reason has been explained earlier. No, if you want to oxidize secondary alcohol, use the same reagent, but you can also use KMnO4 acidified, doesn't matter. Okay. Because once ketone is formed, that's it. It will not be further oxidized. There's no need for immediate separation by distillation. There's no immediate distillation necessary because ketone will not be further oxidized. Okay, another way to prepare ketone is use oxidation of alkene. Okay, now, so when an alkene undergoes oxidation, so what happens is that the double bond is broken or cleaved, and then the O will attach to the C. The reagents has to be KMnO4 acidified. K2Cr2O7 will not be able to do so. This is what was mentioned in the topic of alkene. You can refer to the video for more information. Or you can actually make and bend what do you call this? You can make this, okay, using Friedel-Crafts exhalation. All right. The Cl will be chopped off and it bonds to this. So the H is substituted by this. And this is the reagent and conditions for the reaction. All right. For this one, you call it, it depends on what is here, right? It's something like, if it's only CH3, that means only 2, is 2-phenyl ethanone. Yeah, that's how we name it. Okay, some exercise for you to check which is correct, which is wrong. So for this one, the product of this reaction is benzoic acid, right? So is this possible? Yes. Yes, possible. Okay. You can actually produce this. Sorry, not benzoic acid, I'm so sorry. It's called aldehyde. Yeah, I see wrongly, sorry. Okay. Because you have a H here, so it's a aldehyde. Okay, and then this is not possible because it will form a carboxylic acid instead. This part here will form a benzoic acid. It will not form a ketone. Yeah. Likewise here, you will not form this, you will form this actually. Okay. Because when this is oxidized, this is cut off also, this part here. Yeah, then you will form double bond O, bond OOH. Now, let's look at the chemical properties of carbonyl compounds. The carbonyl carbon is sp2 hybridized. Okay, trigonal planar. Okay, the three sp2 hybrid orbitals of this carbon will form sigma bond with three other atoms of 120 degrees apart. The remaining p orbital of C overlaps with p orbital of O to form a pi bond, which is represented by the double bond. And for carbonyl compounds, they undergo nucleophilic addition. Okay, we shall look at it in detail. So first of all, we understand why carbonyl compounds attract nucleophile. The C atom of the C double bond O group, which is the carbonyl carbon, bears the partial positive charge, as it's bonded to a more electronegative atom. So the electrons are drawn away from the carbon towards the oxygen, which makes the carbon center positive relative to the oxygen. So with a partial positive charge on the carbonyl carbon, it attracts the nucleophile, which are electron rich, to this electron deficient site. And why is it addition? Because the C double bond O is unsaturated. So as long as you have a double bond, it's considered unsaturated. All right. So the susceptibility of the carbonyl carbon to nucleophilic attack is affected by these factors. Electronic factor. The electron releasing alkyne groups or the arrow group reduce the magnitude of the partial positive charge on the carbonyl carbon and decrease attraction for the nucleophile and susceptibility of the carbonyl carbon to nucleophilic attack. So if you have the substituent as electron donating, okay, you are going to make the carbonyl carbon less electron deficient because you donate electrons to the carbon. So it will be less likely to attract nucleophile and hence undergo nucleophilic attack. Where alkyne group release electron by inductive effect, arrow groups do so by resonance. So if you have a benzene ring like this, okay, so the electrons can actually move around the structure. So from the double bond, it can actually move to the oxygen, okay? And then from the benzene ring, one of them can move up, and this one can move up, up, up. So it actually supplies electrons in a way to the carbon and make it less attractive to the nucleophile. Another factor is steric factor. Like if you have bulky hydrocarbon group, it will increase steric hindrance about the carbonyl carbon. So it will hinder the approach of the nucleophile that try to attack the carbon and causes a reduction in reactivity. So from these two factors, electronic, either by inductive or resonance, and steric factor, we have to conclude that aldehydes are actually more reactive than ketone because of the steric group, and also for ketone, they have an extra electron donating group from the alkyne. This is because the carbonyl carbon in aldehyde is actually more electron deficient, as it only have one electron donating group, and ketone has two. And compared to ketone, aldehyde experience less steric hindrance around the carbonyl carbon because it's only bonded to one R group. So in nucleophilic addition, this is the general overall equation of what happened before we look at the mechanism. So remember we say that this is unsaturated. So this double bond will be broken. The pi bond will be broken. Okay, the pi bond will be broken to form sigma bond. So from sp2 hybridized, it will become sp3. from trigonal planar become tetrahedral. Okay, so the H will be attaching here. Sorry, not the H, I'm so sorry. It's a CN and the O with the H. Okay, so they will add to it. 1 plus 1 equal 1. That's addition. Okay, so this is what happened. So this one add, this one add. Same here. The H add, add. So the reagents and conditions are HCN, but you need some amount of KCN as the catalyst. All right. Or HCM again, this is the reagent. Catalyst is the condition, not the reagent. Okay. Or you can have KOH as the catalyst, or KCN and sulfuric acid. All right. Now, let's look at one example before we go through the mechanism. Okay. Yep, the mechanism will be below. Now, this is a 2007 A-level question. Okay, you have cyanohydrines are useful intermediates in organic synthesis. They are made by reacting aldehyde and ketone with HCN, with which a small amount of NaCN was added. So in a series of experiments, the reaction was carried out with different concentrations of the three reagent, and the relative initial rate were obtained. So use the data to deduce the order of reaction. So this is like a revision to kinetics. Okay, so if you compare experiment 1 and experiment 3, where the concentration of the aldehyde is the same, when you increase NaCN by 1/4, yes. All right, from 0.008 to 0.006, sorry, reduce. The initial rate was also decreased by 1/4, from 1 to 0.75. So 1/4 to 1/4, the order of reaction with respect to NaCN is 1. So this is how you actually explain the order of reaction using the data. Okay, this is how you phrase it. For 1 and 2, when you say CH3CHO decrease by 1/4, given that these two are constant, so you choose the experiment. You choose the experiment that shows the changes in the concentration of one variable, but the other is constant. That's how you do it. So from 0.04 times 1/4 to 0.05, the initial rate increased by 1/4. So the order of reaction with respect to this will be 1. 1/4, 1/4. As for 3 to 4, you increase by 1/4. Then the initial rate, when HCN increased by 1/4, this one also increased by 1/4. This one increased by 1/4, which means that to HCN is 0, because from previous experiments show that CH3CHO is affecting. So if HCN is not going to increase the initial rate beyond a factor of 1/4, that means the order of reaction of HCN is 0. So writing the rate of rate equation is just like this. And you don't write HCN because it's 0. Now, describe the mechanism consistent with the rate equation and indicate which step is the rate determining step. So the name of mechanism is nucleophilic addition. You must name it and then state the reagent and condition HCN with trace amount of KCN catalyst. All right. So we talk about how the nucleophile was generated. So KCN completely dissociate K plus and CN minus. All right. So the first step is a slow step. Okay, the detail is in here. Okay. So we will go through now the detail. So in this, let's say if you use KCN as the catalyst, okay, then this will be the mechanism. All right. Your Cn minus is attracted. Okay, so if you have the carbonyl carbon, which is positive, so your Cn minus is a nucleophile generated from the dissociation of KCN. You will attack this one. Please indicate the partial positive and partial negative. And then when you attack this will go up to this. And this is a slow step to form the intermediate. And then this intermediate product will then attack the HCN. Okay, so this become a nucleophile now to attack the H, and this bond go back here to form Cn minus. So the Cn minus was regenerated. So this is a cyanohydrine that was formed. In the case of using HCN, where you use a small amount of NaOH, okay, so the OH minus and HCN will react to form H2O, so it will take away this H and this Cn minus form. Okay, the step here is the same. Okay, and for this step is also the same, but what is different is only the generation of nucleophile is different. Okay, but the rest of it is the same. If you have H2O involved to protonate the intermediate, it will form this. So this intermediate, right, anionic intermediate, will either attack this or it can also attack the water, okay, to form the OH minus. But this OH minus will react the HCN to regenerate Cn minus again. All right. Okay, let's move back. Now, so the next question is to ask if propanone will react as a faster rate compared to ethanol. So propanone is the ketone, ethanol is the aldehyde. So the carbonyl carbon in the ethanol is more electron deficient, as we discussed earlier, as the latter has an additional electron donating methyl group. So we explain using the electron donating group. So the propanone undergoes nucleophilic addition more readily. Okay, less readily, sorry. The carbonyl carbon in the ketone, okay, the propanone is bonded to two alkyne group, experience more steric hindrance also. Whereas the CH3CHO is bonded to only one alkyl group. So propanone will react slower. NaCN role is to produce the central Cn minus in a nucleophilic, the actual Cn minus, sorry. The one that attack the carbonyl carbon first is actually the Cn minus from NaCN because it dissociates completely and form a larger concentration of Cn minus. HCN is only involved in the second step to act as a Bronston acid to protonate the anionic intermediate. So it will provide the hydrogen. That's its role. So from kinetic study of the nucleophilic addition, the rate equation is derived as ethanol Cn minus. This is consistent with the mechanism where one ethanol molecule collides with one Cn minus in the slow step. We need to take note that HCN is actually a weak acid based on the low Ka and only dissociate partially. So the reaction rate is dependent on Cn minus. So if you have a very low Cn minus, it will be slow. So to increase the reaction rate, the concentration of Cn minus can be increased by adding a small amount of strong base. Because when you add a strong base, the H plus is consumed. So by Le Chatelier principle, the equilibrium position will shift to the right to produce more Cn minus, to increase the concentration of Cn minus. Therefore, the reaction rate will increase. So this above reaction, right, is actually simplified to HCN plus the OH minus, forming water and Cn minus. Okay? Or you can add a strong electrolyte that has Cn minus, like KCN or NaCN, because it will be able to complete ionization completely to form Cn minus. The energy profile diagram depicts the nucleophilic addition mechanism. Oh. Where EA1 is bigger than EA2. So EA1 refers to step 1, EA2 refers to step 2. So if step 1 is a slow step, you will expect it to be greater. Then EA2 will be. So EA1 is actually greater than EA2. So that's why EA1, which is a step 1, is a slow step, having a higher EA. To form the intermediate, then the second step is a faster step with a lower EA. And yeah, overall it's an exothermic reaction. Okay. Since the geometry around sp2 hybridized carbonyl-carbon is trigonal planar, the nucleophile can actually attack the carbonyl-carbon from either side of the plane with equal chance to form a racemic mixture containing equal amounts of enantiomers. All right, enantiomers. So the Cn minus, if attacked from the above the plane, okay, it will be this way. And if it below the plane, will be here. All right. Or it can be this also, if you flip it over lah. Why do carbonyl compounds undergo nucleophilic addition but not alkenes? Because the sp2 hybridized carbon atom of the C double bond O group, the carbonyl carbon bears the partial positive charge as is bonded to a more electronegative oxygen atom. As a result, the electron-rich nucleophile, such as Cn minus, are attracted to the electron deficient site. The sp2 hybridized C atoms of the C double bond C do not have a partial positive charge, so it can't attract nucleophile. It only attract electrophile later, yeah, in the second stage of electrophilic addition. So, yeah, that's the difference. So, cyanohydrines are also known as 2-hydroxyl nitriles, just like nitriles. Cyanohydrines are useful reagents in organic synthesis as their formation extend the length of the carbon chain by 1 carbon. So if there's a question that say, oh, there's an extension of the carbon chain, you may want to think about this reaction. The difference is that there's additional OH group in the molecule. So they serve as an intermediate in the synthesis of other organic compounds like carboxylic acid or amine. So cyanohydrines, right, undergo acid hydrolysis to form 2-hydroxyl carboxylic acid, like here. So if there's something like this, you form this, it can be further hydrolyzed to form this. Okay, so this is hydrolysis reaction. You don't call this oxidation. It's not. Okay. Cyanohydrines can undergo reduction using different reagents to form amine as well. For example, you have a reducing agent like lithium aluminum hydride. Okay. You can actually reduce this CH2, NH2 here. So this one, or you can actually use nickel at a higher temperature, 150 degrees. This one can be carried out in room temperature. Yeah, dry ether. But you don't have to state the room temperature condition, no need lah. So what is this answer? So let's track this. The product of the reaction between propanol and hydrogen cyanide is hydrolyzed under acidic condition. What is the formula of the final product? So propanol draw out first, and then it hydrolyzes to form this first. So they react to form, there is a nucleophilic addition, then CnCOH. Okay. Filling the blanks for the reaction scheme. So you can have this undergoes oxidation. Okay. Yeah. With trace amount of KOH, HCl nucleophilic addition, and then lithium aluminum hydride in dry ether. Form this, and then this, you form this. Now look at the reaction of aldehyde to alcohol through reduction. So aldehyde can be reduced to primary alcohol, where ketones are reduced to secondary alcohol. You can use sodium boron hydride to do it, or just simply lithium aluminum hydride, or hydrogen with nickel and heat, that will do. So any of these three agents will be able to reduce the carbonyl compounds back to alcohol, whether it is ketone or it is aldehyde. All right. But for carbonyls, right, only NaBH4. So NaBH4 is only specific for carbonyl. You cannot use it for the rest. Yeah. If let's say the organic compound has both aldehyde and alkene functional group, I will not advise you to use hydrogen because it will reduce both groups. So if you only want to reduce the aldehyde group, just use N8BH4. These two reagents cannot be used to reduce alkene because the reaction involves hydride nucleophile. So the carbon atom of the double bond do not have a partial positive charge, unlike the carbonyl carbon, which is positive. Another reaction is condensation, or we call it addition-elimination reaction. So aldehyde and ketone react with the NH2 of this chemical compound called 2,4-dinitrophenolhydrazine, in short, 2,4-DMPH. So it will form 2,4-dinitrophenolhydrozones and eliminate water. That's why it's called condensation, because a small molecule is eliminated. Okay, so this is a way to test for carbonyl compounds, either aldehyde or ketone. Okay, so when this is added to this, so the hydrazone is formed, C double bond N. So these two, this and this out will form water. Then the carbon is bonded directly to the nitrogen. Okay, so it's called 2,4-dinitro because you have these two, this 4. So this is first phenyl dinitro. So first, second nitro is these two. Yeah, hydrazine. It's called hydrazine here. And the oxidation will be an orange precipitate or orange crystalline solid. Now, so you need to know how to draw the product lah. Okay. In general, where X represent alkyl or aryl group, the compound is known as a primary amine. Its reaction with carbonyl compound results in the formation of carbon-nitrogen double bond, like what you see just now. All right. So this is called amine. And because you have two hydrogen, you call it primary amine. Same for the one below as well. So these two out. Okay. Now, for formation of carboxylic acid, it only involves the aldehyde, not the ketone. And we have certain reagents to test for aldehyde presence. All right. We can use K2Cr2O7 or KMNOH, and we should know the oxidation by now. But, okay, this is what we have gone through, so I will not go through again. Just take note that aldehyde will be oxidized to carboxylic acid because this hydrogen is extracted in oxidation, either as a proton or atom. But you don't see that happening with ketone because they do not have the H that will be, removed in the oxidation process to form carboxylic acid. So this reagent can be used to differentiate between aldehyde and ketone because ketone cannot be further oxidized. Other reagent you can use is called Tollens reagent. This is the chemical formula. It's actually a silver diamine complex. Yeah, diamine silver ions. Okay, so during the reaction, and it has to be alkaline. And what happened is that silver is formed as a product. We call that silver mirror. Reflective lah. Yeah, so this H is taken out, form the water, then NH3 come out. Yeah, don't have to know the mechanism in the syllabus. So only aldehyde, not ketone. Reduce the silver in Tollens reagent to silver. So under carefully controlled conditions, the silver will deposit on the wall as a mirror. That's why we call it silver mirror. Another reagent we can use is called the Ferlin solution. It's actually copper 2+ alkaline. Another name is called Benedict solution. For those students who take bio, you should be familiar with this. Okay, and you need heat. For this, you also need heat. I forget to mention. So both reactions require heating, but not too hot. Just heat will do. Okay, you just need some thermal energy to activate the reaction. So the reaction is very similar to above, where you have the O- form. O- because of the alkaline. So it could be O- Na+ here. Yeah, that's why. If it's acidic, it will be OH, but we use alkaline because only that the reaction will proceed to form the reddish brown PPT, Cu2O. Okay. In bio, they call it brick red precipitate. Here, we just call it reddish brown PPT. All right. So what happened is the Cu2O form, the H come out to form water, then Cu2O. One of the O come out to form here. All right. So this alkaline solution of Cu2+ is actually complex with tartrate ion. Okay, this is not required to know. And then the aliphatic aldehyde reduce the copper 2 to reddish brown, which is precipitated. So it's not applicable for aromatic groups. Okay, it only for Tollens reagent for both, but Ferlin solution only for one, not this one, not this group. So that's how you distinguish lah. All right, you need to know the difference. Aromatic aldehyde and ketone do not react, so you can use this solution to differentiate between aliphatic and aromatic aldehydes. So if you have this, what will be the answer? So let's look at this. Determine the identity of the liquid ABC, given that these are propanol, propanone, and benzaldehyde. So since these are three colorless, so how do you differentiate them? Let's say you have these three liquids in front of you. What appropriate reagents and conditions will you use to differentiate them? So you need to carry out at least 2 tests, can be more than that. So you can try to add Tollens reagent. So with A, because it's an aldehyde, there will be a silver mirror. And there is also a silver mirror for, let's say, wait. A. Oh, this is the result of the test. So this is silver mirror, no silver mirror, right? Sorry. So which one now? So these are the result. I must show you the result. Yeah, Tollens and Ferlins. So Ferlin solution, reddish brown, no reddish brown, no reddish brown. So A component is the propanol lah. Then B is a benzaldehyde law. And C is the propanone. Then for this one, what is X, Y, and Z? So X, OH, then oxidize, then further oxidation to this. Because you don't use KMnO4, so you form aldehyde and not carboxylic acid. Yeah. The next test is formation of triiodomethane. We call it iodoform. Oxidation for carbonyl compounds with CH3CO. So only carbonyl compounds that have this structure undergo oxidation. So this group of compounds consists of ethanol and all methyl ketone. So this C double bond O must be bonded to R here. The R must be either a H atom or another C atom. So it can, if this is H, then this will be the one. If this is R, then either or, okay, will be reacted. So when such carbonyl compounds are heated with alkaline I2, a carboxylic salt will be obtained along with yellow crystals of triiodomethane, CHI3. So this one react with iodine, OH minus, then this one came out to form CHI3, then this one attached with O minus alkaline, so equal Ma plus or K plus. Then I minus is being reduced, then you have water. The oxidation will be yellow PPT. So in general, doesn't matter with aldehyde, ketone, alcohol also can, they will give a positive results, all of this. So this R here, so as long as you have R bonded to C that bonded to double bond O or OH, doesn't matter. So this will react, this one will react, okay, doesn't matter. This is covered under hydroxyl compound alcohol, which we covered already, I think. Yeah, so it's similar law. So next exercise, how many structural isomers with molecular formula C6H12O can give yellow crystals? So they said yellow crystals with hot equals alkaline iodine and orange PPT. So orange PPT means aldehyde or ketone, cannot be alcohol. Yellow crystal means it must have something like this. All right. So since orange PPT is obtained, the isomers must be a methyl carbonyl group. All right. So it can be expanded in different ways. So it could be something like this. Like this. So you can keep on branching out lah. The here or here. So 4 different ways. Benzaldehyde and phenyl ethanone are the simplest examples of aromatic carbonyl compounds. So aromatic carbonyl compounds in general are less reactive towards nucleophilic attack compared to the aliphatic counterparts. This is because the carbonyl C atom in the aromatic carbonyl carbon is less electron division due to the interactions of the pi electron cloud of the carbonyl group and the adjacent benzene ring. Being derivative of benzene, this compound undergoes electrophilic substitution, whereby the carbonyl group is considered to be ring deactivating and 3-directing because of the because of the good overlapping between the pi electron clouds. Okay. So this is a summary of the will not give. Give. So you can refer yourself. To repeat right here, it doesn't matter. This one also can. Even this is H. This one also can, 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 this one also can. Okay, doesn't matter. It may not be CH3, it can be CHI2, CH2I, or even CI3. Yeah. Now, so this is a summary. I will not go through this. Yeah, it's a good summary. Self-reading. And this is the mechanism just now. Okay, so that's about it. You know, maybe I can say refer to last page. Okay, that's it. Thank you. Please remember to subscribe to my channel.